This exercise is called the channel exercise, and the exercise aims to set up a very simple Delft 3D model. We are going to generate first a grid with RGF grid, and in that grid we are going to add a depth using Quicken, and then we follow steps in the Delft 3D user interface, adding the boundary conditions and other numerical settings, and we're going to run the model and analyze the flow results. First of all, this is the user interface of Delft 3D. Consists of a grid tab where you can define the grid and the depth of the model, the flow where you really set up the model itself, a tab called waves where you can make the settings for a wave model, and utilities. And utilities are post-processing and pre-processing tools. An important aspect of this user interface is that you have to work from a working directory. We're going to make that first, and we call that channel. That's a directory here, and in the user interface we can select then that working directory called channel. That's very handy because all the files that we generate are stored over there automatically. The first step is then make the model. Here I provide you with the specifications of that domain. It's a 1 kilometer wide and 10 kilometer long channel with grid cells of with the size of 100 by 100 meters. So the spatial distance, every grid cell distance is 100 meters, a depth of 5 meters, and we're going to apply a time step because of courant conditions of about 1 minute. So first things first, we generate the grid. We click the grid, and there we have the RGF grid software, which is basically generating the grid itself, and the quick in is adding a bathymetry or a depth based on the grid. The first step is then to generate a nice grid with RGF grid. You can see here the user interface of RGF grid, and under operations you can create a rectangular or circular grid. This is the most simplest option, and there's plenty of other opportunities and possibilities of generating a grid here, but this is the simplest way. I think it's a very good first step to do that. So the number of grid cells in M direction, we call that 10. In N direction it's 100, and the delta x delta y is 100, and that's the grid cell size. We say OK. Now you see that this channel going north-south. I don't want that. I want to have a channel east-west, so that means my M direction should be 100 and my N direction should be 10. Here we are. We save the grid, export grid, and we call that 001, for example. This grid is then automatically saved in our working directory channel. With that we can close RGF grid. I really want to quit, yes, and we are going to add a depth with Quicken. Quicken has a similar user interface as RGF grid, sometimes a little bit confusing. We can import the grid over here, import grid, and we can add a depth over here of 5 meters. How do we do that? Under operations you can say combine depth and uniform value, fill missing depth with uniform value. We include all depth points and we give that a depth of 5. So the depth is positive. So the depth is 5 meters, so it means a positive value. If I would impose a negative value here, I would have a negative depth, which is not very relevant for our case. So 5 meters depth. And we are going to save this depth, and we call that 001 as well. If we look into our working directory called channel, we see indeed that depth file was generated, the grid file was generated, and enclosure file was generated. Enclosure file belongs to the grid, and we're going to close Quick-in. We don't need that anymore. We finished the generation of grid and depth, and we return to our main menu. We did do the grid. Now we're going to flow, and we have to define the flow input. This is where you see the user interface of flow input, and if you take all the tabs sequentially, step by step, you can just make your model. In the description tab, you can say, give the model a name, channel setup, for example, and domain. We are going to add the grid here by opening the grid 001. We have to open the enclosure file. Here you can specify the latitude, but we keep it at the equator for this moment. It's very simple. There's also the number of layers. It's a two-dimensional model, so it's a single layer. If we want to have a 3D model, we add some layers over here, but we'll do that later, I guess. Then the next step here is bathymetry. There's two options here. We can create a uniform bathymetry of 10 or any other value. You can fill in 5 here. But what we did before is we created with Quick-in a file, and we opened that file, and it's called 001 dep. And these are all default values. We're not going to touch that. And we are going to the next step. I'm not touching all the tabs that are possible, but later on during this course we will explore more opportunities and possibilities here. The time frame, let's run for 1 month. The reference date is the reference date of the model. Don't touch that. And the simulation start time by default starts at the reference date. And we're going to, the simulation stop time is 1 month later, so we call that 27th of June 2021. And our time step, I explained that before. The time step is bound by courant conditions. Delft3D can deal with courant conditions with courant numbers between 0.1 and 10. And if we then have a depth of about 5 meters, our celerity, so the wave propagation, is about 7 meters per second. And that means that the time step should be between 1.4 seconds and 140 seconds. So let's take 1 minute for that. So this is time frame. Then let's go to processes. There's plenty of processes that we can add here, like salinity, temperature, tracers, sediments. We're not going to do it at this moment. Let's keep things simple. Initial conditions, let's keep the water level at 0. And the boundaries we have to force. So basically what we now have is a 1 kilometer wide and 10 kilometer long basin, but that is not forced by any water level differences or inflow conditions. So we're going to add that. A nice option here is to visualize what we are doing. So under View, we can have the visualization area, and we are going to add a boundary condition. So we have open boundaries, and we are adding here a boundary. So that's the upstream boundary, and here we are adding the downstream boundary. So the remaining boundaries at the north and south here are closed. No flow is allowed to go through that. You can keep this window open, and you see now in the GUI that two boundaries have been defined. We can give that also a different name. We call that upstream. Oh, this is downstream. I'm sorry. Downstream. So downstream is red, and if I go to the other one, this one becomes red, and I call that upstream. So the upstream boundary, I'm going to let flow in there. I'm going to define a current over there. Let's say we can. There's all kinds of time definitions that we can apply by astronomic, harmonic, or time series. Let's go for time series. Let's then define these conditions. So here you can see very nicely filled in already for you the time of the model, the runtime of the model. That's 1 month, as we agreed, and this should be I'll just say 0.7 or so, or 0.8. So flow is flowing in with a velocity of 0.8 meters per second. There's a tricky thing here, because it can be either positive or negative. And when this is defined as positive, it means it is defined as positive with respect to a positive m direction. So the positive m direction, if you look at the visualization area, and you see here on the upper right, you see here, or you see that in the middle here, like the m direction is positive towards the right. So that means if we give positive values at the upstream boundary, flow is flowing in. And that is exactly what we want. Okay, well, if flow is flowing in on the upstream boundary condition and it cannot go out, the basin will fill itself, and it will keep on filling during a month, during the runtime. So the downstream boundary condition secures that the water can also flow out. And we are going to impose also a time series here, a flow condition, a water level flow condition of 0. And 0 is 0 meter with respect to the reference level, where the reference level is the bed level is at 5 meters below reference level, because the depth of the basin is 5 meters. So boundaries, we did physical parameters. Here you can see that you can adjust the constant of gravity. If you want to perform calculations on the moon, you can adjust the gravity values here of the water density values, the roughness values. We just use the default values here of a Chassis value of 65, and the viscosity also. Let's not touch that for this moment. Numerical parameters, also don't touch it. It's default values, and these default values appear to work nicely. There's possibilities of adding discharges here. for example, by pipelines or so, but we're not going to touch that either. Monitoring is more important for this moment. Also here we can make use of the visualization area, and we can add different observation points. And that means that at these points we will have output generated every interval that we will specify later. And we can also add, so these are observation points. We can also add cross sections, so that we have output through these cross sections. Actually, it's nice to add these cross sections near the observation points. So these cross sections, they will generate, for example, the discharge through that cross section, and the observation points will generate water levels and velocities at these points. We can also give these observation points and cross sections different names, but I'm not going to do that at this moment. It is compulsory to define at least 2 observation points. If you don't do that, the model will not run. So it's good to keep that in mind. We don't provide additional parameters at this moment, and we are here. You can see where how the results are stored. So what is the time interval at which the different model outputs are exported to the output. We have 2 types of output conditions. We have the map output and the history output. The map output covers the entire domain, and if we use the same time interval as the time step that we defined under time frame, and that is 1 minute, it means that every minute for all the points everywhere we have output, and that is often much too much output. Your output files will be very large and they become very difficult to handle. So generally the output interval, you take that at several hours or every hour or so. And the history output generates output at the cross sections and at the observation points only. So that's really a very limited amount of data, and there you can define a higher resolution time interval here. So 10 minutes, for example, as long as it is a multiplication of the time step that you're using for your model. So the history interval for high resolution at a limited amount of points, and the map interval at low resolution at the entire model domain. There's also possibility of details where you can say some parameters I want to store in the output and some are not, but let's keep it at default. I think we now set up a model, and we're going to save the model. We can say that just by save all, and if you do that, automatically Delft3D will ask for names to be filled in, and I call them 001. So this is the boundary location, this is the boundary time definition, this is the cross-section file, and this is the, the observation file, and this is the MDF file. So you see that Delft3D works with a lot of files, and I saved them all right now. So if I go to the working directory, I see all these files there. So 001.ops is basically a text file defining the location of the observation points with respect to the coordinate system of the grid. The same holds for the cross-section file. And there's also this MDF file that's called the master definition file. And that defines all the model parameters. That's basically the most important file that connects all the other files into one file. And for example, here you can see the name that I gave to the model. Here you can see the time step, the time, stop time, the temperature of the water by default. So this is a very handy file, the observation file, and here also all the output conditions that I defined. So 10 minutes for the history interval and 120 minutes for the map file. Now, it is possible to just modify in a text editor the MDF file itself, or you can use the GUI if you are just starting Delft 3D user. I would strongly recommend to use the GUI, and that's what we're going to do for this exercise. Remaining files are the BCT file. This is the boundary conditions file, where the boundary upstream and the boundary downstream are defined, and the values of 80 centimeters per second for the upstream boundary and the water elevation for the downstream boundary of 0. And you see here, for example, the start time, and this is the beginning of the boundary, and this is the end of the boundary, and this is the end time, and this is the beginning of the boundary, and this is the end of the boundary. Let's go back to what we did. We have 3 windows open. We made our flow input. We don't need a wave input, and we're just going to start our model and browse then the MDF file, and that's called 001. And let's see if it works or not. So you see, our model takes about 3 minutes to run our model for 3 months, or for 1 month, and that means we can wait for 3 minutes, or we can already look at the results, because it is possible that during the runtime you can access the model output. We do that by QuickPlot. That is a post-processing tool of Delft 3D. It always takes a little bit longer to load that. There it is. We can open the history file or the trim file, so the map file or the history file. What shall we do? Well, let's open the trim file. So that's the entire domain. And here we can see the name of the file, and here all the output parameters that we want to open, or that we can open. Like there's the water level, the depth average velocity. We can open the depth average velocity, maybe that's a nice one. And you see that where there's already 155 output time steps that are generated. And if I'm going to view that, I want to see. I see basically water flowing. It's a vector field there, so the water is inflowing and here it's outflowing. If I zoom in, you can really see that it's going from the water is flowing from left to right. And if you want to look at the magnitude, we can select, instead of a vector, we can select the magnitude here, and we see that initially here it's 0.8. That's our boundary definition, and the flow is slowly accelerating to a little bit more than 84 centimeters per second at the seaward boundary. If we look at the water level, you probably see a similar linearly sloping result, and we can see that the water level at the downstream boundary is 0. That is our boundary condition, and at the upstream boundary the water level is 0.3. Another way of looking at this is we can make a cross section of this, and we do that by switching off the N and filling in here, for example, 6. So we take the 6 line, and if we go to this grid, we can see what we did. We selected basically the middle section of our channel. Now we can do it by just numbers, but we can also nicely do that by visual tools. So it's a very strong tool to select any cross section. And mind you that this is a cross section output at a resolution of the map file. If we look at the water level, then this is the water level. And for example, we can add here the bed level. Give that a black color. We add that to the plot. And then we're zooming in. Zooming in. And this is what we see. So basically this is a cross section of our model domain. Now, of course, this is the water level at a certain moment in time. It's the 27th of May. And we're going to explore whether that's an equilibrium condition or not. We can do that by opening the history file. So we have much more time steps here because it's a higher resolution. And we are not going to evaluate the bed level, but the water level. Gives that a blue color. And we see that it is at 0.3, and this 7.7 is near the entrance. And if we take a point near the downstream boundary condition, that is 95.8. We give that an orange color. We add that to the plot. And we see that that is lower, that is near to 0. So that's indeed a point over here. And if we look, so these are straight lines, and that means that there are kind of equilibrium flow conditions. But in the beginning we see also some disturbance. If we zoom in over there, you see that both lines, they start at 0, at 0 hours. That is also our initial condition that we defined. And that it takes about 4 to 5 hours to stabilize. So then because you suddenly put on the forcing in this basin, you got some disturbance and some back and forth of the flow, but after 4 or 5 hours there's a stable situation where there's a constant flow going on, and the water level is also constant over time. So that's a very a very nice result. I want to leave it at this. And the next exercise, oh no, maybe it is nice to disturb the flow a little bit, because we saw that in the velocities that we had the depth average velocities, we had a very uniform profile, and we almost don't need a two-dimensional model here, but it would be nice to disturb the flow a little bit. So what happens if we put a rock or a groin in this system? And let's do that. So I'm going to go back to the user interface. First, I'm going to check if the model is ready, and indeed the model is ready. So you see that over here, it's finished. There's no errors, and there's a single warning, which is not very relevant here at this moment. So I close this window by file exit. So we're going to add a groin. Where are we going to do that? In the domain. We had the visualization box switched on, and we add a thin dam here. We can also do that visually. We say edit thin dams and edit mode add. We can draw a line here, and that line basically says that no flow is allowed through that line. There's also an option of adding dry points, like rocky systems in our grid, and that means that these are dry points and there's no flow, there's no water allowed in these cells. Well, because we did it, we have to save it again. File, save all, and there's two more things because we added dry cells. That's what we have to define here, and we added thin dams, and we have to define it also here. And it's now saved, and I can run again. This means also that my old runs are overwritten. Maybe not so nice if I want to compare results, so I can also save file, save my MDF as 002. Because my model results are stored with the MDF file as an extension. You see that over here. The first run was called 001, and the trim file is called trim-001, or 3H, the history file 001. If we make the MDF file, if we call it 002, then the old result files will not be overwritten, and we can compare the model results. I also see here a lot of these tree restart files. It's called restart files, and these files are used that if you run a model, you use these files to start another model based on your old conditions, and you see that they are a lot. And where did they come from? I don't like them so much, especially not for our purposes. So under output conditions, on the storage, there's this restart interval. So every 1440 minutes, so 1 day, this restart file is generated. And if we just add a little bit more zeros here, the restart interval becomes very large and no restart files are generated. I save my MDF and I start my file. And again, I can open my file during the run. Oh, I mistakenly run the wrong run because it's not 001, I have to run 002. I open it, there it is, 002. This is also a nice button because we opened the file, but the run is still running. So this button says reload the selected data file. And that means that it's the same data file, but it is updating according to your model progress. You now see the depth average velocity. Indeed, we now not see a nicely linearly moving pattern, but because we added the thin dams and the rock, we see also their influence, because the velocities in the blue area are 0.2, much lower than the 0.8 of the other run, and there's acceleration of the flow in a smaller cross section, leading to velocities of almost 1.6 meters per second. So that's a lot. We can also nicely put that into in a vector field. And that comes to this one, where we really nicely see that behind the groin there is no flow possible, and you see the flow lines merging into the narrower cross section. You can also apply colored vectors with a color based on the magnitude, so that you really see a combination of the magnitude and the vectors over here. And the color bar here indicates the velocity magnitude. Okay, well, thank you for your attention. This is your first Delft 3D model. Try to set it up and try to run it. Try to play with it, and I'll see you back next time.